the charge is higher, the electric field will be higher, the density of the electric field lines is higher. And here the charge is diluted, so the density of the electric field lines is going to be smaller. So the field is non-uniform because this is a case of asymmetry. It's not symmetrical, the charge distribution. Right? So, however, if you look at this surface, the electric flux through this surface is going to be zero. On the top hemisphere of this Gaussian surface, there are more electric field lines entering, but they are bunched over a smaller area. Here there are less electric field lines per unit area that are leaving the surface, but they are spread out over a larger area. So everything just balances out so that the total flux through this closed surface is going to be zero. These are all subtle points, right? So you really have to take this into account. It's just conceptual thinking. You will not find this kind of thinking in any book. No textbook will teach you how to look at problems of this kind unless you do the problems or unless you do my recitations or tutorials. So you really have to be careful on. In thinking, you have to develop this habit of thinking critically. So unfortunately we don't have a lot of time at our disposal now, but I'll try my best to cover up as much ground as we've lost. Imran? So in the previous lecture we discussed electric potential energy, and we defined the change in the electric potential energy as the negative of the work done by the internal forces, which is minus of E dotted with dl as you go from some initial position to the final position, and this is defined as the change in the potential energy. And the example that we took up was of a single point charge of magnitude Q, and we went from one point RA to another point RB along some path. This could be along the radius or some tortuous path, some meandering path, some serendipitous path, right? Any path that we like, even though the field from this charge is radially outward. And we found out that delta U, the difference in potential energy from the final to the initial point, was given by, now if I were to talk about potential energy is between two interacting systems, so I have to place some test charge here. So some test charge is in the field of another charge that is producing an electric field. And the relationship that we determined was 1 over 4 pi epsilon naught Q Qt 1 over RB minus Q Qt 4 over pi epsilon naught 1 over RA. So what this identifies is that this term is simply equal to UA, the potential energy of a charge Q2, Qt, that is inside the field of another charge Q, and the distance between those pair of charges is RB, right? So this is the potential energy at point B, likewise this is the potential energy at point A. So the general rule that we have is that the potential energy due to a pair of charges, right? Remember, it's always a pairwise interaction. So you have a molecule, you just add up the potential energies between the pairs. So the potential energy of a pair of charges in which the mutual distance between the point charges is r, is given by 1/4 pi epsilon naught, the charges themselves, their product, divided by r. Remember, it's not an r square, it's an r. Remember also that this is a scalar. This potential energy, like all energies, is a scalar. When we're dealing with forces like the Coulomb's law or the gravitational attraction, we have an r square term. But this is an energy. It has a 1/r term. So this is the potential energy between two charges of the system which are displaced relative to each other through a distance r. It's a pairwise interaction that we're talking about. Now in physics or electromagnetism, if we take a different test charge, the potential energy of the system is going to change because it depends upon Qt. Now we define a quantity that is independent of the test charge. Like just as the force between two charges depends upon the charges, but if you divide that force by the test charge, you get an electric field. That electric field is produced by one charge. So you get a description of the electric field that is independent of the test charge. Likewise, if you divide this U by Qt, you get a description of a field. You get a field description that is independent of the test charge. You can put any test charge you like inside the field. So now this description is independent of the test charge. It's denoted by V. I will denote it by V. Different authors will denote it differently. I will denote it by V, and it's called the electric potential. Just the electric potential. So what does this mean? This means that if I have some charge, Q, a point charge, that is producing an electric field in its environment, and the electric field permeates space, and I'm at a distance r from this charge, which means one is sitting at the electric field, then at this point there will be a certain electric potential. Alright? And the potential at this point, V at r, is going to be given by 1/4 pi epsilon naught, the magnitude of the charge that is producing the field divided by r. Now if I were to talk about potential energy, I will take a test charge and place it at some point inside the field. Only then the concept of potential energy makes sense. Correct? Because as you remember, potential energy requires interaction. You cannot have potential energy in a system in which there are just solitary charges. So I pick up a test charge and place it at my point of interest. Then I can define a potential energy of this test charge at this point, when it is placed at this point and fixed in its position here. So if my test charge is now Qt, then my potential energy of the test charge and consequently of the entire system is going to be Vr, the potential at this point, times the test charge that I placed at this point. And the analogy that you could keep at the back of your minds is, if you have a force, you divide that force by the test charge, you will get the electric field. Now this electric field does not depend upon the test charge, but the force does. The electric force is Qt, the test charge times the electric field. So exactly the same analogy works here. The potential gives you a description that is independent of any probing charges that you place inside the electric field. So now different points inside space will have different potentials. This point will have some potential, this point will have another potential, and this point is going to have another potential. So we will have a distribution of potential. Now the electric field is a vector field, right? But the potential is a scalar field. Now this is my motivation for the concept of potential, electric potential. Now let's look at the relationship between electric fields and electric potential. Now we know that the change in the electric potential is simply going to be given by the change in the potential energy divided by Q test charge, right? So if you have a point charge, then you can simply take the change in potential energy due to the field from that point charge divided by the test charge, and you will get the change in the potential energy. Okay, but you also know that delta U is the negative of the work done by the internal forces. So you have a minus sign here, and you really want to integrate from E dot dl from some initial position to the final position, right? This is how we've defined the electric potential energy. Now suppose there is some electric field in space, some non-uniform field in space, whatever kind it is, and I take 2 points A and B. Right. And there is a difference of potential between B and A. Delta V is the potential at B minus the potential at A. Alright. Now I know that this equals minus delta U is the negative of the work done, QT. Remember, this is not EDL, this is FDL. Work done, right? Now F divided by QT is just the electric field. So this is minus E dotted with DL. Remember that this is the negative of the work done. Now the work is a force. Force dotted with DL. Remember your previous lecture, but the force divided by QT gives my E. So now this equals minus E dotted with DL as you go from A to B along some path. Correct? Now suppose B is really close to A. So I move this point really close to A. This is some B dash and I move it really close to A. Now this field exists in space. So there will be a coordinate axis. There will be an x-axis, a y-axis and a z-axis. So this vector here, dl, will really have components along x, y and z. So if I look at the electric potential difference between B and A, I can write minus E dotted with, now dl I can write as dxi plus dyj plus dzk. Because the displacement from A to B, which is dl, can in all cases be decomposed along a certain axis. So dl will have a component dx along the I-axis, dy along the j-axis, dz along the k-axis. Alright, this is always possible to do that. Now suppose the point B is really close. So if a point B is really close, the situation that I have is that I can forget about the integration. Okay, so this becomes almost the same as negative of the dot product of E with this displacement. So if the distance between B and A is really small, I can write minus E. E is x component. Now E is an electric field. So it will have an x component, a y component, a z component. And when you take a dot product, you're left with minus Ex dx plus Ey dy plus Ez dz. Now this is the difference in potential between points B and A. Alright? Now look at this expression. When you are going from A to B, both x are varying, y are varying, and z are varying. Now if I take 2 points, and I would like to go from point C to point D, and this is the y-axis and this is the z-axis. Now what I could do is I could first move along the y-axis through some dy, and then I can move along the z-axis through some dz, and I will reach this point dz. If this point d were outside the plane of the blackboard, then I could move along y, move along z, and then move along x. Or I could first have moved along x, then along y, then along z, doesn't matter. If these distances are really small, it doesn't matter at all. Now if you look at this expression, what this expression entails is, I can replace this delta V by dV. That's alright, I can always do that because it's a small change in potential. Everything is small, that's why I've gotten rid of this integration sign. Now if I look at this expression, this means that if y and z do not change, this means that if this term is 0 and this term is 0, this means that I'm only moving along the x direction. I'm making a displacement only along the x direction. I can break up any displacement into 3 orthogonal movements along the x-axis, the y-axis, and the z-axis. Now if I put this equal to 0, this means that my dy is 0. I'm only moving along the x-axis. I'm not moving along the y or the z-axis. Then if this were the case, my dv will become equal to minus ex dx. Minus ex dx when there is no dy or dz. If there is no dy or dz, my dv, the change in potential as I only move along the x-axis, must equal the negative of the electric field along the x-axis into the displacement along the x-axis. So if I move only along the x-axis, that is out of the plane of the blackboard, then if I multiply my displacement with the electric field's component along the x-axis, I will get the change in potential as I move along this displacement. Likewise, dv will be equal to minus ey dy when both dx and dz are 0, etc. So what this really means is that my Ex is really equal to the derivative of the potential with respect to x, and I'm putting these curly signs to show that this is partial differentiation. This means that the electric field along x is the negative of the partial derivative of the potential with respect to x. And this means that there is no motion along the y or the z axis. And I'll give you examples to clarify this. So this is coming out, popping out from the mathematics that we've seen so far. Alright? Likewise, I have Ey, the electric field's y component, equals minus partial v over partial y. The electric field's z component is partial v over partial z. Okay, so we have these three scenarios. What we have is that you take a scalar potential which exists in three-dimensional space. This could be a function of x, y, and z. It is a function of x, y, and z. You differentiate this with respect to x only. These partial derivatives means only you differentiate with respect to x, keep y and z constant. You take the negative, you will get the electric field along x. Let me give you an example. Suppose I have two infinitely charged, very large plates of infinite size. Suppose this is my x-axis. This point is x equals 0. Now, first of all, I know that the electric field in this region is 0. The electric field here is 0. And the electric field here is sigma over epsilon naught pointing in the x-axis. Now the electric field is a vector. It will have an x component, a y component, and a z component. So if this were the electric field, what's the y component of this electric field? What's the y component? 0. And the z component is also 0. So this electric field only has an x component. The electric field here only has an x component, which is sigma over epsilon naught. Now from our previous lecture, if we introduced a positive test charge, we noticed that its potential energy, let me draw a figure here. This separation is L. So this point, this is the x-axis, this is 0, this is L. Now, first of all, let me draw Ex. I'm not drawing a vector, I'm drawing the x component of the electric field, which happens to be the electric field itself. Because the electric field only has an x component, it doesn't have a y or z component. So all of the electric field is along the x-axis. Now, if I were to draw the electric field's x component between these points, here the field is 0, here the field is again 0, and in between the field becomes discontinuous, takes up a constant value and remains constant here. And this height is sigma over epsilon naught. And this discontinuity actually tells us it's a positive discontinuity, so there's positive surface charge here, and here it's a negative discontinuity, it jumps down, so there must be a negative surface charge here. Now this is the electric field. Now if I were to plot the electric potential energy, now let's plot the electric potential energy of a positive test charge that is introduced inside this system through a tiny aperture. Here we have assumed that the potential energy is 0, and in our previous lecture we already saw that the potential energy is going to drop. So here the potential energy is 0. Then the potential energy drops to some minimum value. Remember, delta U is minus delta K. The kinetic energy goes up and the potential energy goes down. Right? And it goes down like this in a linear fashion. This is something we derived from the previous class. The change in potential energy is negative, while the change in the kinetic energy of this object is positive. And this drop from our previous lecture, you notice that this drop is EL. The increase in kinetic energy is plus EL and the drop in potential energy is EL. So the potential energy goes from 0 to minus EL. And then here there is no electric field, so here it just comes out, its kinetic energy does not change because it does not see a force here, so its potential energy does not change when it comes out of a tiny aperture here. So its potential energy remains constant then. So I just put in a straight line here. So this is the graph of the potential energy of a test charge. So there is also, this is minus EL times the amount of the test charge, Qt. Now if I were to draw the potential, the V, the potential, I will just divide this graph by Qt. because the potential is simply the change in the potential energy divided by Qt. So it will just be the same graph. The only difference is that its slope is going to be different. And this point is now minus EL. So I just divide this graph by the value of Qt, I'll get the change, I'll get the potential. Now if you compare this electric field with this change in potential, it all makes sense. If I take the derivative of this graph and put a negative sign with it, I'll get this graph. So this slope is, so here the slope is 0. This graph is 0, which means it's a constant potential. So this region is of a constant potential or an isopotential region. Iso means constancy. This is a constant potential region. In this constant potential region, if I take the derivative with respect to x, this is 0. The electric field is 0. Likewise, in this region, which is beyond L, it's an isopotential region. If I take the derivative of this potential, which is this term, it's 0. And I take the negative of it, it's still 0. So the electric field is 0. In this region, the slope is negative. It's a downward pointing slope. But it's linear. It's the potential is changing linearly. So this slope is a constant. Right? Then I take, it's a negative constant. Then I take the negative of it, it gives me a positive number. Now let's find out the slope. The slope is simply EL divided by L. It's minus E. This slope is minus E. Right? It's just this height, which is minus EL divided by L, which is minus E. Now minus E with the negative gives you plus E. So the electric field is plus E in this region. So this was a simple case in which the electric field was pointing only along the x-axis. But if the electric field had components along the y and the z-axis as well, you can compute these components by simply looking at the potentials. Now the advantage, so this means that if you know the potential, the scalar field, which is the potential, you can compute its partial derivatives with respect to x, y and z, and from it you can compute the electric field. Does it seem easy to compute the electric field or the electric potential? What looks easier? The electric potential actually looks easier because it's a scalar. You don't have to worry about the components of the electric potential. The potential is just a scalar. So it's sometimes easier to compute the electric potential and from the electric potential to compute the electric field by looking at these partial derivatives. Now let's look at some more examples. G. Why this negative sign here? So the derivative, you find the derivative and then take the negative of the derivative. Right. So, but we would like to keep the upper graph is, the electric field is positive. It's increasing in the x direction. It's in the x direction, so it's positive. So this electric field is positive because it's pointing along the x direction. If you have a positive charge here, it's issued here. Here its potential energy will be highest and its potential energy will be lowest here. So the potential energy is dropping. The electric potential is dropping. The convention is that your test charge is always a positive charge. Okay? Now let's use some of these concepts. When you first encounter a definition and some motivation, it might look somewhat frightening and cumbersome. But once you grapple through with application in examples, things become clearer. अचानक सूरज तुलू नहीं होता, आहिस्ता आहिस्ता सूरज निकलता है. ये नहीं होता कि अचानक तुलू हो जाए और रोशनी हो जाए हर तरफ. आहिस्ता आहिस्ता ही सुर्खी होती है, फिर जनाब दिन निकलता है आहिस्ता आहिस्ता. ठीक है, तो दिन आहिस्ता आहिस्ता ही हमेशा निकलेगा. इसलिए परेशान और घबराने की जरूरत नहीं. You just have to be patient. So now let's look at a few examples or applications that bring home this concept of what the relationship between the electric field and the potential is. First of all, I would like to talk about what happens in and around metals. We've already seen this in the context of electric fields. Suppose I have a charged metallic sphere. I know that all the charge must reside on the outer surface because Gauss's law has to be satisfied and the electric field inside has to be zero. Because if there were an electric field, it would produce acceleration of charges and currents will start to flow. But we have a completely equilibrium condition, no current is flowing. So the electric field inside is zero. And we also know that the electric field outside on this perfect sphere is always pointing radially outwards. We know that. So on all points of the surface, any point, the electric field is sigma over epsilon naught pointing radially outwards along the radius. So I can put a unit vector r here as well. Sigma is the charge per unit area on the surface of the sphere. It's all pointing radially outwards. Alright, so far so good. Now there is no electric field inside this sphere. We're going to talk about potentials now. If there is no electric field inside the surface, then it means that the entire volume of this metal is going to be at the same potential. Because if you look here, if this term is zero, then the potential must have a derivative with respect to x, which is zero. If this term is zero, right, zero means each of these terms is zero. This means that the potential cannot change with respect to x. The potential cannot change with respect to y. The potential cannot change with respect to z. So inside the volume of this metallic sphere, the potential cannot change. The potential may not be zero, but it cannot change. It's constant, whatever the potential is. So the electric potential inside the volume of a metal under equilibrium is all zero. So the entire volume of a metal is an isopotential volume. Delta V inside is zero. Potential V can be non-zero, but it does not change inside the volume. Only that ensures that the electric field inside is zero. Alright, okay? Now let's look at what happens outside the metal. Remember, metals are equipotential volumes in equilibrium conditions when no current is flowing, because the electric field inside has to be zero. Now consider the same scenario. A charged metallic sphere where the charge resides only on the outer surface. Remember, sometimes I will draw charges outside the periphery, sometimes inside the periphery, but it always means it's on the outer surface. Sometimes I draw it inside because now I would like to draw something else outside, so I don't want to clutter the diagram. Now what I would like to do, I draw a sphere, a hypothetical sphere outside this volume. This is a sphere and this hypothetical volume is concentric with the metallic sphere. And I would like to find out the potential at this point. Suppose this is at a radius RA. Now I draw another sphere outside. And this point is at a radius RB. And what I'm interested in calculating is the difference in potential between B and A. I'm interested in calculating VB minus VA, final minus initial. Now I know that VB minus VA must equal the negative of the work done by the electric field divided by the test charge. So it's negative of, so I'm going from A to B, negative of this integral, E dotted with dl, where dl is some path. So I have some path between A and B, and dl's are the infinitesimal displacement vectors that make up this path. So I compute the electric field at each point on these paths and find the dot product with each tiny path. So this is a local dot product, and then I integrate. In Gauss's law, you have an area here. So you find the dot product of the electric field with the area. Here you find the dot product of the electric field with a tiny displacement. Right? So if I blow up this path a little bit, at each point I will have an electric field that is pointing radially outward. So this is the electric field at this point P, and then I have a tiny displacement which is tangent to the path, dl, and then I take the dot product of this EP with dl, and then I move along the path and then add up all of these tiny dot products to find out the total change in potential as I go from A to B. In Gauss's law, we use surface integrals. Here we're using line integrals. Slightly complicated, but you'll get the hang of it, don't worry. So now this is E dot dl. Now we know what the electric field here is, and we know what the electric field here is, and we know what the electric field at any point on this path is. At any point on the path, the electric field is pointing radially outwards. So here it's going to point like this, here it's going to point like this, here it's going to point like this. So the electric field at all points is pointing, any point is pointing radially outwards because of the spherical symmetry of the situation. Remember, it's not a point charge, but it's a spherically symmetric distribution of charge. So still the electric field is pointing radially outwards. The same argument that we've used so many times. Hence, VB minus VA equals minus A to B. Now my E is, I need to find out the electric field, which is given by 1 over 4 pi epsilon naught. Suppose the total charge is Q. Now this electric field comes from Gauss's law. Q, capital Q, which is the total charge on the sphere, over R squared. R squared, because if I'm at different R's, my electric field is 1 over R squared, into the unit vector R, which specifies the direction of the electric field, dotted with dl, the tiny dl's that make up the path. Now each of these, this is the direction of the unit vector R, is the same as the direction of the electric field. So each R dotted with dl is the component of dl along the radial direction. This is simply dr. We've already seen that. The component of any displacement along the radial direction is just some dr. Okay, it's the displacement along the radial direction. So what I have here is VB minus VA VB minus VA is minus 1 over 4 pi epsilon naught. Q is a constant. From A to B, R dotted with dl is dr divided by R squared. Okay, you can refer to your previous lecture notes to find out why have I written R dot dl equals dr. This integral is minus 1 over R. So I have Q over 4 pi epsilon naught 1 over R, from where R is going from RA to RB. VB minus VA equals Q over 4 pi epsilon naught RB minus Q over 4 pi epsilon naught RA. So due to this distribution of charge, a metallic charge sphere, this is simply VB, this term is simply VA. So now what we observe here, if all of that charge Q was situated at a point and we were at a distance r from this point charge, then the potential from the point charge discussion is given by Q over 4 pi epsilon naught r. But what we've seen here is that instead of a point charge, if we have a distribution of charge like this, so it's no longer a point charge, rather a metallic shell, or it could be a metallic sphere, doesn't matter. The charge is on the outer periphery. Here the charge is on the outer periphery as well. In all of these cases, if we are at a distance r outside the metal, and this charge is still capital Q, then this potential at this point is still going to be equal to Q over 4 pi epsilon naught r. So no matter where that charge is, whether it's concentrated at a single point, it's on the surface of a charged object, it could even be uniformly distributed on an insulating sphere, the potential is given by the total charge divided by 4 pi epsilon naught r. And this is only true outside the surface of the sphere. Inside the surface of the sphere, the potential is going to be constant, not zero. So let's draw, okay, so this is a very important point. Let's draw a nice graph that actually illustrates this. This is a sphere of radius capital R. Small r. E. If I were to draw the electric field as a function of r, small r, where r goes from 0 to infinity, I know that the electric field inside is, what's the electric field inside? It's a metallic sphere, charge on the surface. What's the electric field inside? 0. So the electric field inside is 0. And what's the electric field outside? Is it going to jump? Is it going to be discontinuous here? Yes. And what's the field outside? What does its dependence look like? 1 over r squared. Be confident. So it jumps to some value because there's surface charge here, and then it jumps down like this. And this is given by 1 over 4 pi epsilon naught capital Q, where Q is the total charge over r squared. And then it drops like this. Now if we were to draw on the same graph the potential V of r, let's not worry about the potential inside. This is capital R. This point is capital R. The potential outside is going to be 1 over 4 pi epsilon naught Q over R. So outside, it's going to be fall off as a hyperbola. Not as a parabola, but as a hyperbola. So it's going to fall off gently as 1 over R. So here the potential is going to fall off as Q over 4 pi epsilon naught small r. Now the potential has to be continuous, because if the potential is discontinuous, if this is discontinuous, then this electric field will go to infinity. So the potential has to be continuous, which means that this has to be a finite number. Partial v or partial x is finite, partial v or partial y is finite. So the slope cannot change suddenly for the potential. Otherwise the electric field will go to infinity. So at this point, the potential is capital Q over 4 pi epsilon naught capital R. So this point is capital Q over 4 pi epsilon naught capital R. And inside, the potential is going to remain constant. So whatever the potential is at the surface, it's going to remain constant within the surface. So it's going to remain fixed or clamped at this value. So the electric field inside is 0. However, the potential at the boundary is given by the potential at the outside at the point small r equals capital R, and in the interior of this metal, this potential is going to remain constant at this value. Alright, so I can take a couple of questions. Yes? The potential is going to remain constant, it's going to remain whatever it is here everywhere. So it's going to be the same here everywhere. There's one more question, yes? Right. So you can use the analog of the Coulomb's law to calculate the potential, but it's easier to calculate it if you know the electric field. Alright, so have a good eat break. There's going to be a homework after the eat break. I've already uploaded the tutorials and the recitation for next week. So inshallah see you after it. Thanks a lot.